It's time for Maths with Mr. Thomas.
Ho ho ho! Here we are at the end of this chapter, chapter 11, which looks at the double angle and the addition formulae. We started off way back many years ago looking at cos A plus B, sin A plus B, and so on, and we've worked through this chapter. This is the review lesson, which is just a recap of all the key points. It doesn't include every single slide or every example. You may wish to just watch this before the exam to make sure there is nothing you have forgotten. If there is anything you're unsure of, look back at the individual lessons. So, what's this chapter all about? Well, we started with the addition formulae, and I was saying that there is an equation that you are given in the exam. The formula that you have is cos A plus B equals cos A cos B minus sin A sin B, and you're also given cos A minus B, which is cos A cos B plus sin A sin B. What's the point of this? Well, if you wanted to work out something like cos of 75 without a calculator, it's difficult to do. But what you could do is you could rewrite it as cos 45 plus 30. And you can expand it, and you can then evaluate that using your exact value triangles. So you don't have to remember the formulas in the exam, but you do need to know your exact value triangles or the table off by heart. And you also need to know your sine graph, cos graph, and so on. So, example 1, we had to expand cos g plus h. So doing that, we had cos g cos h minus sin g sin h. We were just using these formulas here and thinking, right, we're replacing a and b, and we're replacing it with g and h. So just take this formula at the top, where it's a plus b, and replace the a with g, and the b with h. Doing the same thing, we're n minus 35. Well, we're subtracting, we're replacing a with n, we're replacing b with 35. So really, we've got this here, and we replace the a and the b. We did some more examples going back the way. So if we have it where it has been expanded, when we want to put it back into the brackets. So because we've got a cos 170, cos 70, and a sine 170, sine 70, and there's a minus in the middle, we know we're looking at this top equation here. So putting it back into the brackets, we're going to have cos something plus something. And the two somethings are obviously 170 and 70. Work that out, take it a bit further, use cast, work out the exact value. 240 degrees lies here, cos is negative, it's 60 degrees away, so it would be negative 1/2. We worked through quite a few examples. This was the same. We had to go back the way again to put it back into brackets. Again, because you've got cos cos, sin sin, with the plus in the middle, it's going to be cos something minus something. And the two somethings, we've got pi over 2 and pi over 3. So cos pi over 2, take away pi over 3, pi over 6, and that would work out to be root 3 over 2. Again, you need these exact value triangles. You need to know them off by heart to allow you to work something like that out. Other examples, you had to expand cos x plus pi over 6. So this time when we expanded it, well, we can work out what cos pi over 6 is because we know these exact value triangles. So after you expand, you can replace cos pi over 6 with root 3 over 2, and you can replace sine pi over 6 with a half. Doing that, take out a half as a common factor, and you get a half bracket, root 3 cos x minus sine x. And the same for the other one as well, for cos pi minus theta. You're replacing the a and the b here with pi and theta, so you'll end up with the right hand side, but in place of a you've got pi, in case of b you've got theta, and once you have that, well, you can work out cos of pi and sine pi by thinking about your trig graphs. Doing that, and it gave you negative cos theta for your answer. After that, we had cos A equals a fraction, cos B equals another fraction, and we had to find out the values of sin A and sin B and cos A minus B. Matthew, what do we always think about when we get that? The triangle's good. Well done, Matthew. So if you're ever given something like that, where cos A is 12 over 13, draw a right angle triangle, put in an angle, just call it A, and you know cos A is 12 over 13, so the adjacent divided by the hypotenuse will be 12 over 13, and just use Pythagoras to work out the missing side. We had cos B as well, so draw another right angle triangle, call that B. This time we had cos's 3 over 5, so we would have 3 over 5. And again, use Pythagoras to work out the missing side. From there then, we know A and B, we know all the sides in each triangle, so it's dead easy to work out whatever we're asked for, sine, cos or tan of A or B. So sine A, you would have 5 over 13, sine B, 4 over 5, and so on. To work out cos A minus B, expand that, and then sub in the values, and simplify. So we get 56 over 65. Other examples, well, we had to use 15 degrees as 45 take away 30. Similar to that first example on the first page, it said it's difficult to work out cos of 75, so you would be using something else like 45 plus 30. So for 15, it's 45 take away 30, so we're wanting to expand that, sub in the values, and then use the exact value triangles to work out what they would be. And if you do that, then you would end up with root 3 plus 1 over 2 root 2. Always check the answer, check what you've got to get down to. Here we had a rational denominator, so we then had to rationalise the denominator by multiplying the top and the bottom by root 2. Doing that gave us the answer. Lesson 2, we then moved on to look at sine A plus B. Similar to cos A plus B, you can also expand that. If you expand sine A plus B, you end up with sine A cos B plus cos A sine B. And if you're subtracting, then you subtract here as well. We went through very similar examples, so expanding sine u plus v, well, because it's u plus v, it's something plus something, so it's going to look like the right-hand side here. If we were expanding sine p minus q, well, it's something take away something, so it's going to look like the right-hand side in this bottom formula. We went back the way as well, and we also wrote 105 as 60 plus 45. Expanded that then, so we're writing the 105 as 60 add 45, expand it, and then sub in the values, because we can easily work out sine and cos of 60 and 45. So from that, we would get our answer. Simplifying, we had sine pi over 2 cos pi over 6 plus cos pi over 2 sine pi over 6. Going back the way, we're thinking it's sine cos, cos sine, so we know it's going to be sine A plus or minus something, and because there's a plus in the middle, well, we know it's going to be sine something plus something. So we're adding pi over 2 and pi over 6, and we get down to our answer. Just remember, when you get down to sine 120, if you're doing it without a calculator, think about cast, think about the quadrant. Well, it's sine, it's 120 degrees, sine's a positive there, and it's 60 degrees away from 180. So that's the same as sine 60, and you can use the exact value triangles to work out what that would be. Again, another one, if we had sine x is 12 over 13, cos y is 3 over 5, what do you always think about when you do that? Triangles! Exactly, you want to think about the triangles. So from that, draw a right angled triangle, call one of the angles x, and sine opposite over hypotenuse is going to be 12 over 13. You can then use Pythagoras to work out the missing side. Cos y, cos is going to be your adjacent over hypotenuse, so this time it's 3 over 5. Use Pythagoras, this side's 4. If we want sine x minus y, expand that using the addition formula, sub in the values of cos x and cos y and so on, and you get 16 over 65. We had to simplify sine 3 pi over 2, take away pi. Lots of these examples are very similar. For this one again, you expand it. You then work out the values. So sine 3 pi over 2, well, thinking about that in terms of degrees, it's 270. So for that, you'd be using your trig graphs here. Here. You would be using them. Sub in the values, and you would end up with negative cos theta. Other examples that started to get a bit trickier. Again, though, you just had to expand. But we're expanding and then we're subtracting what we get when we expand the sine x plus 30. From there, you had to just use your exact value triangles to work out the value of cos 60 and sine 60 and cos 30 and sine 30. And once you are down to there, you can then simplify. There were other examples like that. Look back to the lesson if you are not sure. From there, we went on to the harder examples. So for this one, we were told that sine ACB was equal to this fraction here, but we had to prove it, we had to show it. So to do that, we were given the triangle, we had to work out the missing side, so we weren't given AC and we weren't given BC, but we could use Pythagoras to work them out. We then expanded sine P plus Q, we subbed in the values, and we got down to the desired result. Oh yes. Look back to this example again if you're not sure. We did more examples. This one here was proving that tan 3a plus tan a was equal to this. So for that, well, tan, if you remember back to last year, tan is equal to sine over cos. As Lewis Kidd says, it's a sin to put cos on top. Find some way to remember this. You are not given it in higher. You do need to know it. So it's a sin to put cos on top. Well done, Lewis. I like it. So we're replacing tan 3a with sine 3a over cos 3a, replacing tan a with sine a over cos a. From there, well, you need to have the same denominator if you're adding. So here we're missing a cos a, so multiply the numerator and denominator by cos a. Here we're missing cos 3a, so multiply numerator and denominator by cos 3a. From there, you get the same denominator, so we can add the numerators. And here, this step, well, because we've got sine, cos, sine, we're thinking about this. So which one would we use? Well, if it's sine, cos, sine, we know it's going to be sine A plus or minus. And because we've got a plus in the middle, we know it's going to be a plus here when we put it back into sine A plus B. A and B then were the 3A and the A. Work that out, and we again get down to the desired result. There were more examples, but example 4 was finding the exact value of sine p plus q. This one was a bit trickier, but it's the same idea. We know we've got point A, which is 6, 8. So in other words, you come along 6, you go up 8. You're forming a triangle here if you're drawing back to your origin. So you've got that OA, and you can use Pythagoras to work out the length. With B, you know you're going along 12, you're going down 5, so you can use Pythagoras to work out the length of OB. From there then, you know that you can expand the sine p plus q, and you can easily work out sine p cos q cos p sine q. Sub in the values, 63 over 65. After that, we then looked at something else that this chapter focuses on. As well as the addition formulae, we also look at the double angle, and we see that you can write sine 2a as sine a plus a, and if you expand it with the addition formula, you get down to this, which you can then gather your like terms. So we've got 2 sine a cos a. With the cos 2a, again, you can write it here, you can expand it, because we've got cos, it's cos squared, sine is sine squared, and using the formulas from last year in this box, you know that sine squared is 1 minus cos squared, so you can write it as that. Cos squared is 1 minus sine squared, so you can write it as that, and you get down to these other formulas. Basically, to sum that up, you get down to this, which is given in the exam. Anybody that is super geeky may wish to go on and get some formulas for cos squared a and sine squared a. You get additional formulas there, which may help you if you get to a really hard example. But we went on to some examples, so write down formulas for sine 4x and cos 10x. Using double angle, well, if we've got sine 4x, you need your formula to be sine 2 times something. So you think 2 times what is 4x? Well, it's 2 times 2x. So here, 2 times what? The what is going to be the 2x. So you're replacing a with 2x. So it's 2 sine 2x cos 2x. Do the same thing with cos 10x. You need 2 times something, so it's 2 times 5x. That therefore will be cos squared 5x, take away sine squared 5x, and again you can use the other formulas as well. We went into more examples, so if we're simplifying 2 sine pi over 12 cos pi over 12, well, we're replacing the a in this equation here with pi over 12. So that can be written as sine 2 times pi over 12. 2 times pi over 12 is pi over 6, and sine of pi over 6, use the exact value triangles to work that out, and you get 1/2. More examples. We had sine x was 3 over root 10. Again, Matthew, what do you always think about when you get that? Triangles! Brilliant. Thinking about the triangles. So draw a triangle. You've got a right angled triangle. Call this x. And sine is the opposite over hypotenuse. So we now be 3 over root 10. Use Pythagoras to work out the missing side. And from there you can easily work out cos x by just looking at it. So the adjacent over hypotenuse. Sine 2x, you need the double angle formula. So sine 2x would be 2 sine x cos x. And you can work out sine x. Work out cos x, or basically just look at what we've found so far. You can go further as well by working out cos 2x. It doesn't matter which formula that you use. I'm just using cos squared a and sine squared a. Using that, sub in the values and simplify, so negative 4 over 5. With sine 4x, again a bit trickier, but you know that's going to be 2 times 2x. So it's sine 2 times something, so you can write it as 2 sine 2x cos 2x. And the sine 2x was really our answer for B. Cos 2x was our answer for part C, as you can see here. So we just sub those values in, and you would end up with negative 24 over 25. Other examples, tan theta is 1/4, and you have to find cos 2 theta. So for this, Zayad, what do you use? Good, you use the triangles again. This is very common. If you are given sine, cos, or tan, and it gives you a fraction, like 1/4, 3/5, root 7 over 12, whatever, you just draw the triangle, label the sides that you have to know, and use Pythagoras to work out the missing side. Cos 2 theta then, well, cos 2 theta, you can use one of these formulas here. Again, doesn't matter for this one which one you use. I'm just using 2 cos squared A, take away 1. Working that out then, and you get down to 15 over 17. Example 6, prove that sine A plus cos A all squared equals this. Again, one of the questions that comes up a lot, asks you to prove something. Don't just start off writing this out and then writing a load of nonsense. Start with the left-hand side, and you know that this is your answer, so that is what you want to get down to. So sine A plus cos A all squared is sine A cos A times sine A cos A. Multiply that out the way you multiply out your double brackets, the way you normally do and have been doing for years. Simplify that. And sine squared A plus cos squared A, well, sine squared at cos squared is 1, and 2 sine A cos A, think about the double angle formula up here. 2 sine A cos A is equal to sine 2A, so you can replace that. Example 7, we want on to some of the harder examples. If you have 3A as 2A add A, prove that sine 3A equals this. So sine 3A, first of all, you'd write as sine 2A add A. Expand that using your compound angle formula, and then after that you can change the double angles, sine 2A and cos 2A, with your single angles using the formulas up here. So doing that, you sub the values in, multiply out the brackets, but really what you're wanting to do is you want everything in terms of sine. So because you've got a cos squared, well, you know you can replace that with 1 minus sine squared. Multiply the brackets again, simplify your like terms, and you do get down to the desired answer. The last bit in this chapter was trig equations involving double angles. So if you ever have a trig equation, like sine 2x add cos x equals 0, if you see sine 2x or cos 2x, and there's something else in terms of sine or cos, you want to replace sine 2x with one of these formulas. Sine 2x, you can only replace it with 2 sine x cos x, so do that, and then you can factorize. If you factorize, you get down to something times something is 0, so you can then get your values. Cos x would equal 0 here, and sine x was negative 1/2. Solve both of them using cast or using the graphs, using your exact value triangles, and then sum up all the values that you would have. This one here was very similar. Again, we've got sine 2x, replace sine 2x with 2 sine x cos x. Doing that, you then factorize. Once you factorize, it's something times something is 0, so you know this is 0 or this is 0. Get the values, solve them using the graphs, the triangles, and so on, and you get down to your values. Once you get down to cos 2x, though, it's a bit trickier because you've got 3 formulas, and you're thinking, oh no, which one do I replace it with? Well, you want to look at it and you're thinking the rest of the equation is in terms of cos. So you want to replace it with the one that's just in terms of cos. Do I? Yes. So with this one here, cos 2x would equal to cos squared A, take away 1. Obviously, you don't write A, you write down x. So replace that, and once you get down to that stage, you gather your like terms. So you've kind of got like a quadratic with an x squared, an x, and a number. Factorize that, so go off to the side and write down 2x squared, take 3x plus 1. Factorize it, you get 2x take 1, x take 1. But you know it's not x, it's cos x that you have. So you would factorize that to then get 2 cos x take away 1 and cos x take 1. Solve both of them, and again you get down to your answers. Anything you're unsure of with solving trig equations, look back to the trig equations chapter. I go into it in more detail over there. Solve 3 cos 2x equals, well again you've got cos 2x, so we need to replace that. Because the rest of the equation's in terms of sine, replace it with 1 minus 2 sine squared A. or x. So for that then, you sub that in, multiply out the brackets, again you get down to a quadratic. Once you get down to something that looks like a quadratic, you can factorise it. So if you factorise something times something is 0, solve the first one, solve the second one, and again you get all your answers. Example 9, write down the equation of each curve. Well, writing down the equation of the curve should be easy enough. You know you're going between 3 and -3. There's one cycle of the sine graph. For cos 2x, you know that equation as well. You should be able to get the equation, and then from there you want to find out the points of intersection. To find the points of intersection, use simultaneous equations. So because they're both equal to y, they're both equal to each other, and you get down to one of the equations from the other examples. Once you get the values of x though, you should really sub them in and get the values of y. That is a very quick recap on this chapter. If you think you're quite confident with it, try the review exercise. Anything you're unsure of though, maybe look back at those individual lessons. Best of luck! Woo!